All right, thank you very much for inviting me and organizing this workshop. So this, I haven't actually worked extensively on the ADMM at all. I worked a little bit on actually more alternating linearization methods with Don and Sichin Ma, who are both here. They've continued more work on ADMM. I haven't done much since, but then there was this one period of the time when I worked with my student and another colleague on a very specific setting, and we just came up with this ADMM and alternating linearization scheme. And because the setting is so specific, we did not really, publicize it very widely, and we did not talk about it that much. But I thought this is a perfect workshop to present this work, even though it's a few years old. And especially, for example, if theoretical results are known, then it would be nice to see where it fits in the known results. And if theoretical results are not known, then it's also good to know. So anyway, so as I said, it's a very specific setting, and the results are not all that impressive or unusual, but still we had to work them out when we wanted some theory. So, so here's I'm describing the setting. I'm assuming that a function that I'm trying to optimize, so there are some constraints that are easy. Is this the pointer? This is the pointer, okay. Right, so there are some constraints that are easy. They're convex, they're nice, maybe simple bounds and things like that. And the function itself is what actually used to be known as the composite function until this new composite form became popular in ADMM. So it is a function of two other functions of x, okay? In some form, it doesn't have to be basically any specific function, but we will make some assumptions. So here, there's this decomposition into two blocks, and basically we're considering two block functions. One is this function when the second term is fixed. So we fix the x here. This g of x becomes a constant. What happens here? And then if this becomes fixed, what happens here? So we have these two blocks. And now we're going to make assumptions on these blocks, essentially. And the assumptions are that these blocks are nice, smooth functions, for one thing. But more importantly, that they're actually both convex over x. So somehow they're easy for us to deal with, and we can solve them. And then they're bounded from below. So just kind of standard assumption and smoothness and whatever, but most important, convexity. So there is a very strict structure. Otherwise, without assumption of convexity, almost anything can be written this way. But this is very specific. All right. So we will basically exploit that fact by just constructing a very classical approximation of the original objective function by using these two blocks. So these are the two approximations. They're both convex. So we take x bar as a fixed value. Then we take this first block function, which is in principle anything but convex. I mean, it's any function, but it has to be convex. Then we take the gradient with respect to the second block at x bar. So it's a fixed gradient here, a fixed vector. So this is a linear function, and this is your kind of quadratic term. We'll see where ADMM comes in there, but we're not only using ADMM. This is actually an approximation of the original function with using the gradient of one of the blocks. And the same thing you can do with the other, obviously just the other direction, right? So we use these two quadratic approximations in our algorithms and our proofs. Okay. The first example, just to set things where we are. The first example is the standard, sum of two objective functions, right? So if you just have the sum of two nice convex functions here that we're trying to optimize, then these two quadratic functions are nothing else but the classical sort of alternating linearization approximation, where the first function is not fixed, the second one is fixed, and you take the gradient. So basically, you approximate the second function by a quadratic. This quadratic should be, mu should be small enough so that g is over approximated the true g is over approximated with quadratic function, but f is fixed as it is, and this gives you a over approximation, a nice over approximation of the original function, right? And if you minimize this, then you can show convergence of the method, because this gives you a reduction in the original function, reducing this. Same thing with this. So this is just, I'm showing that if in case of the sum, it is a very simple standard approximation that people have used. Now, we don't have to have a sum. We can have a product of these two functions. The only thing we need is that not only the two of them are convex, but they're also non-negative. Otherwise, fixing one is going to kill the convexity of the other. But then again, you can just do this simple approximation. So you have the product here, but one of them is fixed. So now you have a convex function sitting here, and then a linear function here, linear plus quadratic term. And same thing here. You have a convex function sitting here, linear plus quadratic term. So if you can minimize these easily, then this helps you optimize the original function. More generally, you can have a function that is affine, right? So the bunch of basically functions, each of them is affine, produces your vector, then g of x can be affine. You can take an inner product of them, and you can have some kind of a constant here, and you can optimize the sum of squares. And if you fix one of them, then what remains is a quadratic function. Okay? So this is kind of leading more to our specific application of interest, which is basically this one. So this is a more general form of writing what I had before. Well, not necessarily, yeah, more general. So now assume you have a system of quadratic equations. So this is a quadratic equation. This matrix does not have to be symmetric. And you're trying to solve the system of quadratic equations. Instead of solving that, you can replace it with the least square approximation, right? And this is a fairly common problem in many applications. We're looking at a specific application that I'll talk to you about, just for kind of explaining where we got our algorithm from and where we got the ideas. But in general, this is a very general setting which fits into what I just described to you. And here, just to be more specific, you can write these two quadratic functions, approximation. Well, they are now quadratic. I mean, they're basically, this is a quadratic function. This is a quadratic function because you fix one side of x and it becomes quadratic. This is a linear term. This is, again, a simple quadratic term, right? So the approximations by fixing one variable and the other are two quadratic functions. And this is the form of the gradient. And they're very similar, except for m here is present as transpose or not. OK? So essentially, the point is that taking these approximations allows us to approximate the original function by very simple quadratic ones. And there is a nice structure that can be preserved also in this approximation. More generally, you can have some right-hand side, some additional linear terms, and you can add some regularization parameter to your function. This is fairly obvious. So more generally, we can have this fourth degree term plus other things that are nice. All right, so I'll start with ADMM, and then I'll go to the actual alternating linearization method. So ADMM here would be, and I'm switching back to the previous general notation just for simplicity. So this was our general notation, right? We have a function of two functions. So we had originally the function of x, which is h of f of x, g of x. Now I'm doing the splitting. So x equals y, and then this depends on x and y. I write the augmented Lagrangian, which is like this, right? And then I can use this augmented Lagrangian in a very standard, straightforward ADMM framework. So I'm going to minimize this. I'm going to minimize this. Then I'm going to update lambda. OK. So just what I want to sort of, this came out of our work for the simple convex composite. These ideas came out of the simple convex composite functions with Don and Sechin. We noticed basically that augmented Lagrangian and these kind of linearizing functions, they have a lot in common. And when you think about it, I mean, you can see it right away. The only difference between this function and this function is that instead of lambda, you have the gradient here, right? And you have the different gradient here. But other than that, it's the same function, essentially. So if I did not have this constraints here, if it was an unconstrained problem, and if instead of updating lambda here, I would update it after this step and this step. So I'm updating it only once, but I could. There's a symmetric version that you could update it basically once after minimization over x, once of minimization over y. If I did this, then this form would be equivalent to this, because the update to lambda would actually happen to make it equal to the right gradient. And you can get it out of basically optimality condition for the Lagrangians. So if you optimize the Lagrangian over x and plug in optimality conditions and see the update for lambda, you will get the fact that the next lambda is going to be the right gradient. Okay? But we're not doing this here, and moreover, what's more important, there's constraints here, and once there are constraints, optimality conditions don't make gradient equal 0, therefore we cannot use it. Why do I stress this? Because when you actually know that lambda is the gradient, you can prove a lot more about the method than when you don't. I mean, when you basically, lambda is just some vector that has good properties. All right? So here, we wanted to use it because it's not really costing us all that much. And but first so we tried both methods. First we considered the augmented Lagrangian, and I'll talk about the other method in a second. And we were able to derive the following result. If mu is small enough, as usual, then the iterates. So the first result is just convergence in a kind of a weak sense that the Lagrangian itself is converging to some optimal solution. And then there's a rate of convergence for a subsequence of the iterates, actually, again, in somewhat a weak sense, in the sense of the gradient. But OK, it's not, because the function is non-convex, so it's not necessarily weak in that way. So these are the basically optimality conditions that we're aiming for. And we're converging to satisfying these optimality conditions in a subsequence, so in Lyman sense, with the rate of 1 over square root of k, which is the right rate for the gradient to converge, basically. OK. So now, to compare, we can have an alternating linearization method, which means that instead of updating lambda, we directly compute those gradients and plug them in. They're not exactly expensive, so why not do that? I mean, because it depends on obviously, it depends on the functions, but in our application, at least, it wasn't very expensive to compute the gradients. So we did this, and so it is a still alternating scheme, but it uses the explicit form of the gradients that we can compute. And then, so we have these two Q functions. Sorry, I don't know where this came from. So it uses these two functions, and essentially, what we need from mu, as usual, is this sort of condition. So I'm minimizing, alternatingly, I'm minimizing one approximation than the other. To make sure that I'm making progress, I want to look at the function values at the new iterates and make sure that they're less than the over approximation. This is, again, standard proximal method kind of technique. So if I do this, and this is satisfied, then I'm fine. I have a convergent method, which allows me, this is the key thing, which allows me to choose mu adaptively. And we know that in practice, it makes a huge difference if you can choose your step size adaptively, because mu dictates the step size, essentially. And we could not do it with ADMM, just simply because we are not guaranteed a decrease, because lambda is not the gradient. But here, we could do that. And so this is makes practically a big difference. In theory, it makes a relatively small difference, but in practice, it makes a very big difference. So so basically now we have a convergence result for this, which is similar. It basically says that so we have the sequence converges to a stationary point of f. So it's better because now we're converging to a stationary point in a very specific sense, not into these KKT conditions. Furthermore, well, the ones that were written, but yeah, but basically it's the same thing. We're converging to satisfy first order optimality condition. This is a sublinear rate. Okay? So theoretical results are comparable, but the difference again is that we're allowed to choose mu differently. Okay. So this is the comparison. Oh, right. There's a difference also that when we're showing this, the decrease and the convergence, we can show the convergence in primal function for ALM, but only in augmented Lagrangian. So convergence is somewhat weaker. Okay. So this is the comparison. How does it work? Well, this is just a silly example, and unfortunately, my student created it, I think, for his thesis, and I don't have access to the actual number of iterations it gave, but I thought this is just cute. I mean, Rosenbrock function, everybody knows. It's exactly in the form that we want. It's quartic. So you can split up this variable into two different variables and then optimize alternatingly quadratics. Very simple. And you get a fairly good convergence here. I mean, if you see in Rosenbrock function, if you just use a first order method, which essentially this is in a way, but it's better than a first order method. So if you just use the first order method, the method is terrible for the Rosenbrock function. But here it nicely goes and kind of curves the valley and converges where it should in some reasonable number of iterations. Not like Newton method, but reasonably close to that. Okay. So how much time do I have?
It's like 12 minutes.
Okay, perfect, right. So I'll just fairly quickly go over this application. This is how we started working on these algorithms because we had the problem at hand, which is called risk parity portfolio selection problem. It's a fairly interesting and not particularly necessarily very difficult problem, but it was not really, considered. I mean, not many algorithms were considered for it, so it was an interesting problem for us to look at. So what is the portfolio? I mean, this is just a motivational slide. It says that the typical portfolio selection that kind of balances out risk and return, puts a lot of emphasis on return and maybe overall risk, and the typical portfolios basically that may have performed well in the past have terrible setbacks in bad years, like this is 2008 when we know there was a crash, and a lot of basically public pension plans have lost a lot of money, and that's not good because obviously this people's livelihood depends on it. So there is, after 2008, essentially, there's been a lot of emphasis on, I think, in quantitative finance on risk parity. So the concept of risk parity is very simple. You don't care about the returns at all. You only look at risk contribution of every asset in your portfolio, and you just simply want to diversify the risk contribution. So each individual risk contribution of every single asset has to be the same. That's what it is. So what is the risk contribution of an asset? So if sigma is your covariance matrix and x are the weights of your of your contributions to different items in the portfolio, right? So this is your x is a vector of investments in the portfolio. Then individual risk contribution is essentially this. It's how much you invested in a particular item or a particular stock or well, particular asset rather, times its risk contribution, which is this. This is the overall risk, and this is the risk. This is, it's a matrix times the vector, and then you take its ith element here, and basically ith column, and this is your ith element, right? And this is the risk contribution. So this is a constant for everybody. So you can basically, if you want to make these things the same, what you need to make the same is this. So everybody, for all I and j in the portfolio, you want the same thing here, okay? So you see how it's already working out. We have a quadratic equation here, right? Equation and quadratic. All right, and essentially, if you have the standard kind of, I forget what is it called, long only scenario, which means that you're only, so you're not shorting any assets. So x is between 0 and 1 and you don't have any constraints, so it is allowed to be anywhere in between 0 and 1, then it's been shown that such a solution always exists and can be actually found by solving a very nice convex optimization problem. Okay? But this is usually not what people want in asset management. They want either to put constraints, so some assets should not be invested more or less. And also you may want to short assets, so that means you may want to allow X to be negative. In which case, there could be up to 2 to the n minus 1 solutions, or there could be no solution to this, depending what X. So if X is in principle allowed to be anything between minus 1 and 1 for each X, you could have that many solutions, but if X is constrained more, you may have no solutions at all. So one formulation that was offered was to just minimize this subject to constraints on X and see what happens, right, where it gets us. We argued that a better formulation, we did argue in one of our papers that a better formulation is easier to solve. They're both, you know, basically sum of squares of, I mean, they're both quartic, but just this function is much more complicated. Okay, I don't have to do this. This is just giving an example of particular set of assets which says that, yes, risk parity gives you much better risk distribution than, you know, other standard portfolios. Okay, so this is the original formulation. We've suggested this formulation. The difference is basically we're just introducing a variable theta that has to, in principle, equal to all of these. If the actual risk parity solution exists, if the objective function reaches 0, they're both equivalent. If it doesn't, they're actually not equivalent. This seems to produce better results in our experiments. Right, but in principle, there can be multiple local minima and so on. So the functions can look like this. If the gradient actually is 0, if the solution is not at the boundary, so yeah, I did not want to emphasize here is the constraints, right? So the bounds on X and the fact that you want to invest 100%. So these are the standard conditions, and that's why our constraint set, as I said, is simple. It's simple to use it, to optimize over it. Okay, so this is what function looks like. The function looks like if you reach actually local minimum in unconstrained sense, you're at a global minimum. You can show that. So if gradient is 0, you know that your problem is solved. And you found risk parity, but you may not have risk parity solution. Therefore, you may have local minima at the boundary. You can do other things with it. You can, so I will kind of skip this part, but there are many things you can extend it to. First of all, you could look for risk parity combined with minimum variance overall. So if there are multiple risk parity solutions, which ones actually gives less risk overall? You can do group risk parity. So you actually group assets, and then you do this by groups. It gives you a slightly different formulation, but again, in a similar thing. You can do risk parity with respect to factor models. So instead of the assets contributions, you look at factors. And again, it gives you a different sort of formulation, but again, it has the same form. So in all cases, you end up with basically solving this sum of squares of quadratic functions, okay? Which perfectly fits our setting. That's how we started looking at this ADMM framework and alternating linearization. So we're comparing several methods here. The partial linearization is essentially the same as alternating linearization, but we just only linearize one part. Why we did this? Because we thought it would be cheaper. It might be worthwhile. This is the alternating linearization, the method where we can do backtracking over mu, because we know the gradients. We use the gradients. This is ADMM in its pure form, and this is actually augmented Lagrangian. So we just take an augmented Lagrangian and solve it by solving multiple quadratic functions, optimizing quadratic functions, basically in a kind of block coordinate descent manner. The instances here are small, but we've tried some, larger ones as well. It's just because, your typical, collecting interesting data in finance, you don't usually get huge instances. But you see the convergence. Convergence is not really about instances, it's about how fast you get solutions. And so essentially here you see that augmented Lagrangian converges quite fast in terms of major iterations, but to solve subproblems, you need to have a lot of work, so you have to solve a lot of QPs. This is for different accuracies, and there's a lot of QPs. Whereas ALM and ADMM are much more efficient. ALM, however, is still way more efficient than ADMM for a very simple reason, because you can do the step size adjustment. So basically, it's whereas here we had to pick mu small enough. And the same thing here. Again, this is converging really fast to a very good accuracy of solution. And this is the case where there is risk parity. This is the case when there is no risk parity. So they're two different cases. And this is a slightly larger result. And again, this is basically, the convergence is super fast. You can see here it converges just in a few iterations and gets good accuracy. And that's essentially, all there is I have to say about this. Basically, we found this interesting problem. We looked at it. We tried to come up with a good method for it, and we just naturally kind of augmented Lagrangian or ADMM or alternating linearization thing came up, because the subproblems are quadratic and very easy to solve and easy to implement. And then later on, we realized that this can be actually used for power flow. Optimal power flow model, because they also have quadratic equations there. At the time when I was working on it, a colleague of mine said that they started using augmented Lagrangian for it, so we didn't pursue it. I don't know if that has become a standard or they've published really good result, but I know that, optimal power flow problem is a more complicated problem in general. So about risk parity specifically, we actually verified that we're getting global minima in many cases because we also considered the SOS relaxations of this, because it's a quartic polynomial, so you can build some kind of, the polynomial relaxation, right? And then you can show in some cases that you have actually reached a global solution because there's no duality gap. So it's just that the method actually works well in terms of finding global solution, but there's no guarantee of that, of course. And that's that. Thank you.